That seems interestingly large. Brighten that up a bit. How's that? Well, you can't really read. Let's actually write it up there. Let's see how that looks. Well, I feel like it's always too bright. I can sit in the dark, and it seems. Thoughts? This or this? Option one, yeah. I mean, I guess it's light outside. It just feels. I feel like I'm going to show a class movie or something. Okay, that'll be all. What else do I need to do? Start with that. Okay. It's always weird being in a new room. Let's see what else. I feel like I'm forgetting something important. I'm sure I'll remember eventually. Let's see. Why is my sorry, you know, first week of class, it's always trying to write yourself what you're doing. Oh, there we go. All right, it's the new time. I guess we should get started here. Welcome. Cool. This. Go back to the 6, 7. I feel like something is interesting here. Let's try. There we go. Okay. Oh, there's something strange here. Sorry. Oh, nice. The views. I always forget about this. Let's do that. Okay, cool. I can see it just maybe. There we go. All right, welcome. Hi. For those of you that don't know me, my name is James. For those of you who do know me, my name is James. You can call me James. You can call me Mr. Parmenter or something else like teacher, or I don't know. You can call me professor. I'm obviously not a professor, but that's a title people like to use. So you're welcome to use that as well. But just call me James if you're comfortable with that. So let's, before we get going with all the math, and I'm assuming, actually I'll ask, I'm guessing you all talked about maybe some antiderivatives yesterday, maybe started to look at area under a curve with rectangles. Okay, I'm seeing some head nods, some head shakes. Sounds like one of the classes did, one of the classes didn't. That's fine. We're going to do that anyway. But before we get going, let's talk a little bit about the kind of logistics of the class. And something I want to point out, because I didn't know this when I was a student, but something you can do that I feel like always makes my life easier, and I should look there because I can look there, is that for your Canvas classes, if you click on these little dots here, which I heard someone called like the shish kebab. Have you heard this before? The little 3 little dots, like the vertical, like the 3 lines are called like the hamburger. The 3 dots I heard someone say the other day is like the shish kebab. Anyway, not important. You can change the title of this. So I have called it Co-21B, and I've written Tuesday, Thursday, 3 p.m. so that I remember where it meets. But if you want to write, and like for these other classes, I'm in the Canvas for. I wrote 17B with Dedell, so I know who's teaching that class. But you can change yours to be whatever you want on there. So I also wrote the CRM because I find that information useful, but you could write whatever you want. So just go play around with it when you have a chance. I highly recommend writing something that is useful to you on there. Let's go ahead and take a look at the Canvas. Next week, the homepage will not be the syllabus. The homepage will be the modules, where anything important will actually be. Just like last quarter. For those of you that were in Co-21 last quarter, it's the same, right? We're doing everything's the same. The modules are where you find the stuff. And specifically in the modules, you will find some useful links, like to the class attendance form, which I'm going to be asking you to fill out just like last quarter, and I'll explain how to do that again. The link to the Zoom, if you want to join via Zoom, you're certainly welcome to, as a couple people are. It's great. You can come to class via Zoom, or you can watch the video recording later on. My office hours, which we'll talk about in a second. Grant's website, which is always linked because Grant's website is always very useful. And then Kuba's 21B website, which also has a lot of homework problems with solutions and practice tests. It's a great resource as well. And finally, my website, which is not useful at all, but there's a picture of my cat there, so you can go look at that if you want to. But really, there's nothing worthwhile to be found on my website, except for maybe a handout occasionally. And then here's where you'll find the recordings from class and the written notes that I will write here during class. And then some other handouts, like some derivative rules that you should be aware of from 21A. And there's a couple different handouts I hear, and that's actually, you can click on those if you want to. Sure. I keep looking at it. It's such a habit to look up there, but I know I can look right there. I just have to actually do it. So here are some derivative rules that you can take a look at later on. The usual kind of things, the power rule, the chain rule, the quotient rule, the product rule, and then some trig derivatives and some exponential derivatives and logarithmic derivatives. And then on this other page, we have some other derivatives to know, which I came up with a little bit later, which have, for example, also the logarithmic and exponential rules and their chain rule versions and their different base versions. And then we also have the inverse trig function derivatives. I think that's pretty much. And then there's some other stuff down there that you may or may not want to read. I thought I had some trig identities on here, but I guess not. Oh yeah, there's a couple trig identities as well. So anyway, you can take a look at those. The derivative rules, you are going into 21B expected to know how to differentiate pretty much anything. So we might spend some time practicing that if we have the time to. I would encourage you all to make sure you know these rules, because again, your teacher is going to be like, yeah, you know how to differentiate all this. So that's something that you are expected to know. And a lot of what this class is going to be is undoing those derivatives, trying to go back and say, if this is the derivative, what function did that derivative come from in the first place? That's what we're going to spend most of today talking about. And then, yeah, it's weird. Sorry, like for some reason this screen isn't showing me like everything that's showing me. Like somehow it's slightly less, which is strange. I'll have to figure that out later. Sorry. And then, so yeah, that's all the useful stuff on Canvas, in my opinion. And then on the syllabus page, we have the usual class things I need to say, but are kind of boring. And really, the most important things are, if you're enrolled in the class via Schedule Builder, you signed up with the CRN, then you have to do the things. The things you have to do are, 1, attend and fill out the attendance form, and 2, do the weekly reflections. The way this class is based, passing is based on attendance and doing the reflections. So attending is how you pass the class. So let's go through the things, and we'll kind of get a little bit more into the details of how that works. And we'll talk about the other stuff as well. So there's a link to the Zoom as well. If you need to find it, if you're coming via Zoom, that's totally fine. I encourage you to come whichever way works the best for you. If you're not feeling well, definitely come via Zoom, or again, watch the video later. As far as reaching me, the best way to reach me is via email. You can also call my office phone and I will pick up from there, or you can come to my office if I'm there, or you can find me in office hours, which is probably the best place to find me in person. This is when and where I will be. I can read them. You can also read them Monday, Wednesday, Friday, 10 to 11:45 in Dutton Hall, 2058. And Fridays just from 10 to 11. Monday, Wednesday, Friday from 2:15 to 3:45 in CADS, which is the Center for African Diaspora Student Success. Anyone is welcome to come there and see me. That's in the South Silo on the upper floor in room 270. And then Tuesday, Thursdays from 10:45 to 11:45 in C class, which is the Center for Chicanx Latinx Academic Student Success, which is in the second floor of the Memorial Union. And then finally on Tuesdays and Thursdays, starting next week in the math drop-in, because math drop-in is not open this week. But all the other office hours are this week. You can come find me wherever I am, whenever I am. As far as grading for this class, let's go. So again, the grading part only applies to the people that enrolled via Schedule Builder using the CRM. If you signed up filling out the Google form or by emailing me and asking me to add you, the grading part does not apply to you, and you should totally ignore the grade that you see in Canvas because it doesn't matter at all. But for those of you that did enroll via Schedule Builder, this part does matter, so pay attention. Pass no pass class, it's based on attendance, which is worth 70% of your grade, and the reflections, which is worth 30% of your grade. And sorry, brain. A passing grade is 75%. As far as doing the things to record your attendance when you come to class, or when you come to class on Zoom, or when you watch the recording within 2 weeks of the class date, then you will fill out this form. Not that form. Clicked on the wrong thing. Now I keep looking up there. I can't help it. So if we go back, sorry, those are the reflections. Let's go to the form. Here's the attendance form you will all fill out. Even so, I should say, you have to do this if you are enrolled in the class, but I also would really, really appreciate everyone doing it, because part of the funding of the academic assistance and tutoring centers comes from the number of students we serve and being able to report that data to other entities. So having a record of all the people that we serve is important. So if you could all please fill this out whenever you attend, it would be really useful to me and my supervisor and her boss as well. So do it because you like the AATC and you want us to continue serving. We're going to still continue serving students, but it helps us out. So please do fill this out whenever you come to class. As far as filling it out, you'll enter your UC Davis email there. So mine would be jjparmenter@ucdavis.edu. Getting that right is not super important. Your student ID number is important. Make sure you get that right. And then your name as it would appear on Canvas, first name first, last name last. Please do write both your names, because I go sort, this all goes to a Google Sheet, and then I look at the Google Sheet, and then I look at Canvas and I enter your attendance data into Canvas so that you can see what your attendance looks like if it matters to you. And it makes it easier for me to do if your name is written in there the way it appears in Canvas. So please do that. And then what class you're attending, obviously Co-21B, how you attended, and then the class date that you are marking attendance for. So if you were watching this video, say on Friday, the date you would fill in would still be April 2nd, not April 5th. Oops, that's not the right thing. Which is, by the way, a palindrome, 4224. Well, I mean, kind of, if you don't count the 2000 part. Please write the year, all 4 digits. Sometimes the year comes up as like 0000, and I'm like, oh, that's not the right year. And it just, I do some sorting with dates as well. So if you can please enter the data correctly, it will make my life easier later on. And I know you want to make my life easier, so thank you so much. And then you would submit it. I'm not going to submit it because I don't want to have that data show up in places I don't want it. As far as actually filling out the attendance form, you can find the attendance form either in Canvas right there, or if you look in the modules, you can find it right there. And you can also find it by scanning this QR code. I can put it there. Maybe not. So if you want to scan this right now, fill it out, you're certainly welcome to. I'm gonna put this up here, maybe. Sorry, pardon my closeness. And I can really, what I usually do is put one right here. And then I make it so you can see the thing. Back. Yeah, but don't love how. So you can scan that, fill it out. It's pretty straightforward. Please do it whenever you attend class or whenever you make up an absence I do require that you make up any absences within 2 weeks of the class date. So if you missed today's class and you're making it up, you would need to do it by April 16th. And more importantly, you would need to fill out the attendance form by that same date. I think it's pretty reasonable. 2 weeks seems fair to me. Yeah. Okay. Let's get through the rest of it. So hopefully everyone has been able to scan that. If you wanted to, I'm going to go back to the, I'm going to try to go back to the things. Seems like it is not wanting me to do that. Cool. Back to the syllabus. Also, if you have any questions, you are welcome to ask them, please. Or if I've written something that seems hard to read, which is not atypical, please don't hesitate to ask for clarification. I know my writing is mediocre at best. So if something looks like a 3, but it's really a 5, or an 8, and looks like a 4, just ask for words that are also hard to read. Please ask. I will try my best to write nicely, but sometimes I'm trying to write so much that I write a little fast and it can be hard to read whatever. Okay, let's see what else in here. So grading. Right, if you're absent, you can make up the absence. You can also find the videos on YouTube, but I will also post them in Canvas. About the class, if something outside of class is impacting your success in math, please don't hesitate to talk with me about it. I want to be a resource for you. If something is said in class by anyone, including me, that makes you uncomfortable, please talk with me about it. Or if it's me specifically and you don't want to talk with me about it, you can talk to my supervisor, who's a lovely person. Her name is Jen. She's easy to find. Or her boss, Sarah. Or you can fill out the AATC feedback form. You can also go to one of the retention initiative centers. It's usually not an issue. I say this because it's good to cover all your bases. I don't imagine that's going to be an issue. But again, if something really does come up, please don't hesitate to talk to someone. I'm here to be a resource for you and to be helpful. So that. As far as the class is concerned, you're all here at the time of class. You know when and where we meet. But it does meet Tuesdays and Thursdays from 3:10 to 4:30 in Olson 125 for those of you that are on Zoom and might not know where the classroom is or are watching the video later. Most classes, I will show you examples. I will show you how to work them. I might have you work on stuff with each other on your own. I might walk around and look at things. Hopefully that's okay. You see the cursor? Maybe. And then what else? Please come prepared to work on math problems. You should all have a writing utensil and a thing to write on. I'm of the opinion that math happens by writing things down. That's how you really learn the stuff. Also, I should ask, for Parlax's class, is there homework that's assigned? Is it due? Yes? Good. How about for Fanjang's class? Assigned and due? Awesome. So you should do all the homework. I'm going to say it like 10 times. You should do the homework, you should do the homework, you should do the homework, because doing the homework is how you're going to learn. You should do more than the homework, really, if you have the time. But definitely, especially since it's being collected and graded, there is obviously incentive to do the homework. But you should do the homework. Can I say it again? You should do the homework. One more time, you should do the homework, because that's how you're going to learn the math. I can say a lot of things here, and you can listen to me say them, and some of that might get imparted to you. But really, the way you're going to learn the stuff is by doing the math on your own and then asking someone, what's going on here? I did this, but I have questions. So I can't recommend enough doing math as much as you can on your own. That's why I will try my best to have you do math on your own in here with each other. It's challenging because we have a hybrid environment. So I feel like when I do that, it kind of leaves out the people that are on Zoom. So it's a balance that I will try to find. But I'm going to try to have you all work on problems together and on your own so that you have more practice practicing the math. Let's see what else here. Accommodations. If there's something I can do to improve your ability to succeed in this class, or the class it is a co-class form. It seems like it's written wrong, but it is right. Please let me know. If it would help you, chances are high that it would also help other students. If you have formal accommodations at the Student Disability Center, please let me know as soon as possible so we can make sure that you are getting what you need. There's a process for There is a process for you to have your accommodation letter sent to me through a secure portal, which I've received a few of. It will not give me any of your personal information. I feel like, is that actually true? I feel like there's a name there, maybe. Just the list of specific accommodations that you are entitled to. Zoom, I think we're in the world of Zoom now. We know how Zoom works. Some notes about the class. If you're enrolled in the class, it's for one workload unit that counts towards graduation. And no, sorry, that doesn't count towards graduation. It counts towards being a full-time student. If you need a unit because you're short a unit and you're not enrolled in the class officially, you can enroll in the class and we can get you there. But if you're other than needing a unit, there's not really a good reason to enroll in the class if you aren't already. I always say this, it never happens. You can use the discussion tab in Canvas to ask questions, and then myself and other students can write responses. I think it's a lovely way to have a discourse, but it's only happened like once in the last few years. So you could try it, it'd be great, but I won't hold my breath. And then as far as the rest of this, just talking about kind of how math classes work in general, the stuff you learn is connected to the stuff before it, and usually things build upon each other, which means it's really important to stay up to date with what's happening in class, because if you miss something, the stuff after it's usually building on that, and it's kind of hard to see what's happening if you don't have the foundation from before. So I really, really, really can't stress enough, can't emphasize enough to do as much math as you can, as often as you can. I'm aware you have other classes as well. Obviously, you have to find the balance of spending time on your other classes too, because they are also important. I would say math is the most important, but you know I love math, so I'm going to say that. But yeah, I mean, do as much math as you can so that until you've at least got it down. That's kind of what I would say. Successful students usually spend 10 to 20 hours a week doing homework, practice problems, and studying for math 21B. That's maybe, I mean, it depends on who you are. It's more for some people, it's less for others. You can get more help in office hours from other math specialists, which we can see when their office hours are here on the AATC math section. If you scroll, you scroll way down, scroll. We get to the very specialists. You can see Claire. She's via Zoom. If you, oh well, I think you have to be enrolled in her class to actually see that. I feel like that's new. That wasn't there, I think, when I looked earlier today. But you can find myself, Grant, and Sarah in various places across campus. If you're looking for help, usually one of us is available at some time of day that'll be helpful for you. It might not always be me. Sarah is great. Grant is great. We're all happy to help you with 21B. Yeah. All right. Are there questions about anything? Anything that, not anything, anything that I've talked about so far? I'm supposed to wait. So they teach you to wait. Not good enough though. Okay. And then as far as people on Zoom, you're also welcome to ask questions. You can, I meant to, sorry, let me do one quick thing here for the people on Zoom. You might have already found the attendance form in Canvas, but if you didn't, here is the link to the attendance form for the folks on the Zoom. And then if you have questions, you're welcome to type them in the chat. If I don't see them, or I don't see them right away, you're also welcome to unmute yourself and say words. It might scare me. That's okay. I've been scared before. I'll live. But yeah, please do ask questions if you have them. It's totally fine to type them in the chat. Just be aware that I might not see them right away because I'm not usually looking at the chat. All right, let me. All right, I'm really good at manipulating this here. Go. Let's close that. Let's bring the other thing back. Sorry, I'm always not sure which way I'm going across this here. All right. So by the way, also you can find the syllabus for the class, like the actual math department syllabus. Let me show you one more thing, just because I think this is actually useful. There's lots of useful things. Well, there's another useful thing I want to tell you about too. Two useful things. Thing one, if you go to the math department website, with math.ucdavis.edu, you go to courses, you go down to syllabi, you can see what you're supposed to get taught in the class you're taking. It doesn't mean the professor is actually going to adhere to everything on this list, but it's a pretty good guideline for what you will probably be seeing in your 21B class or whatever math class you're looking at. So you can see we're starting with antiderivatives and then area under a curve, estimating the area, and it just goes on and on and on and on and on. And you can see if we look far enough, no, we can't. Oh yeah, there's some notes down here about like what you might cut or not cut, depending on if you're teaching the class and you've run out of time because you didn't do a good job of planning things out. But that's there for you to look at. Like, so when you take 21C, you can go like, well, what am I going to learn in 21C or 21D or 22A or 22B or whatever math classes you might take. All the syllabi are on there, and they're pretty set. Oh, and I didn't mean to close that. The other thing I want to show you, which I think is just neat, well, not just neat, I think is neat and useful. Yeah, sorry, one sec. So I will link this in Canvas because I know I haven't yet, but there's a really useful, I think, where'd you go here? Lots of graphing things, but where's the one I want? Where's the one I want? 3-month sum. So this, I think, is really cool. It shows you can kind of pick whatever function you want. So if you pick something easy like 9 minus x squared, and then we can kind of move this around. I can zoom in. And then you can kind of pick however many rectangles you want by sliding this around. And you can approximate the area under the curve using right endpoints or left endpoints or midpoints if you scroll this to the right place. I just think it's kind of neat to actually be able to really quickly see what this area under the curve estimation idea really looks like. We're using rectangles to estimate area under the curve, and you can use a few rectangles and be off by a lot, or you can use a lot of rectangles and have a really good estimate of the actual area under the curve. That's really the whole kind of idea with using Riemann sums and rectangles to estimate areas, that eventually you get the limit of that estimate to get the actual area. We'll talk more about that, but I'll definitely post this link in Canvas. I really recommend playing around with it. Like if you have some questions about like using 4 rectangles or 6 rectangles to estimate what the area under the curve, using right endpoints or left endpoints, throw it in there and see what it actually looks like. It's certainly going to look better than anything I could draw. So yeah, it's a useful tool, and I will definitely make sure it's easy for you to find in Canvas. But before we get there, we have to talk about antiderivatives, because eventually what we're going to see is a connection between finding the area under the curve and using the antiderivative of a function to calculate the area under the curve, which is kind of neat that it works that way. To do that, we have to talk about antiderivatives first. So let's see, it's 3:36, and we're here until when? 4:30? Seems kind of late, but that's when we're here till. Let me grab the pens that I know people can see better if I actually write with them. I think I need to get some new pens. I think I was saying that last quarter. I still haven't got new pens, but these ones are a little bit thicker, so hopefully you can see better. I will say again, if you need me to clarify something I've written, please just say so. You don't have to raise. You be like, hey James, I don't know what you wrote. Or also sometimes I write things up here and then I move the paper up there, and you might like to see that. Just let me know. I will happily move the paper back down so you can see what I've written. Well, let's go ahead and write some things down. That's not what I want. And this desk is weirdly like someone was peeling up off the top of it, which is kind of strange here. So let's see, we are in Co-21B, and today is April 2nd. Yeah, you can see this pen's going to last real long. So let's talk about antiderivatives. This curse is not my favorite. I believe this is chapter 4.8, but you know what? If we look in the syllabus, it says, yeah, section 4.8. You're welcome. So let's see here. Sorry, my brain is braining. So let's start with some examples. We want to find the antiderivative. So I'm never sure if there's a dash in that word or not. Sometimes I feel like I write it that way, sometimes I don't. We're going to find the antiderivative of f of x equal to x cubed. So when we say antiderivative, what we're really asking for is what function has a derivative equal to x to the third. Well, it's probably something like x to the fourth, because the derivative of x to the fourth is 4x cubed. But I'm off by a factor of 4, so I'm going to have to divide by 4 to fix that. So it looks like, and so antiderivative notation is always kind of a pain until you get to the integral symbol. For now, what we'll typically do is if you're taking the antiderivative of a lowercase f of x, we often write the antiderivative as uppercase f of x. So we would say that capital F of x is equal to 1/4 x to the fourth, because the derivative of that is equal to x cubed. Now, I could also add on any constant I wanted. I could add 2 or 3 or 7 or pi or e. And any of those things have a derivative that is 0. So what we usually do when we're finding an antiderivative is we say we could add on any constant. And let's check. The derivative, well, the 1/4 constant multiple hangs out. The derivative of x to the fourth is 4x cubed. The derivative of any constant is 0. And oh yeah, that's going to be exactly x cubed, which is our little f of x. So what that shows us is that 1/4 times x to the fourth plus any constant really is the general antiderivative of f of x equal to x cubed. And the reason I say general is because there are technically an infinite number of right answers here. You could add any constant, which there are an infinite number of, and have a correct answer. So this is the family of antiderivatives, or the general antiderivative. So I should say this is the general. Sometimes we'll have initial conditions, which will then require us to solve for C to find a particular antiderivative. But for now, we're not doing that. So this kind of leads us to a rule for anti-differentiating powers of x. I typically call it the anti-power rule. Which says the following. If our function, f of x, is x to some power p, then the antiderivative, capital F of x, is equal to, we're going to add 1 to the power and then divide by that new power. Just like here, for x to the third, we made the power 1 larger and got x to the fourth, and then divided by the power of the new power, which was 4. And I typically like to write this as x to the p plus 1 divided by p plus 1. And then, yes, we're going to add on a constant. Or if you prefer, you can write it as 1 over p plus 1 times x to the p plus 1. Let's see. It's really the same thing either way. It just depends on which way you prefer. And this works as long as p isn't equal to what number? What value would p have to have that would make us end up dividing by 0? Right. So p can't be -1. But this rule works for any other power of x. So for example, maybe For example, if our function f of x is, say, x to the fourth plus x to the 1/2 minus x to the -7th plus 2, then we can find the antiderivative using this anti-power rule. Each of these powers of x, I'm just going to add one to the power and then divide by the new power. So for x to the fourth, I'm going to get x to the fifth divided by 5. For x to the 1/2, I'm going to get x to the 1/2 plus 1, 1/2 plus 2 halves, which is 3 halves, divided by 3 halves, minus, okay, -7 plus 1 is -6. And we're getting less negative if we're adding to it, divided by -6. And then something here that doesn't look like it has a power of x. Technically, it does. We could think of having x to the 0th power there. Or we could use, I want to say, what's the word I'm looking for? I want to say common sense. I feel like common sense is the wrong word, though. But we know from 21a that if you take the derivative of something times x, like 3x or 4x, you just get that constant. So if the derivative is a constant, the antiderivative is that constant times x. So here we're going to get 2x. The derivative of 2x is 2. And then we need a plus c. And I probably wouldn't be able to let myself leave it like this without doing a little bit of simplifying because it just feels too unsimplified. I would write this as x to the 5th over 5 plus 2/3 times x to the 3 halves. And then minus a minus becomes plus 1/6 x to the -6 plus 2x plus c. You might notice that I kind of easily or kind of without reason go back and forth between writing it as a fraction times a thing versus the thing divided by a number. There's no real rhyme or reason there. Sometimes I like writing it one way, sometimes another. It's not specifically required to be written. You can do it either way. I could have just as easily written this as x to the -6 over 6. I could have just as easily written this as 2x to the 3 halves over 3. It doesn't really matter, but sometimes it just feels better to write that way. So don't worry about which way you're writing, is what I'm trying to say, in the longest way possible. All right. Why don't you all try? So this notation gets tedious, and I might as well get you used to seeing the way people are actually going to write it. So eventually, even though we haven't defined the integral yet, people kind of just start using the integral symbol because we who are teaching it are like, well, we know this means the antiderivative, and the students are going to see it too. So let me show you what I mean. So this means, what I mean by this is this integral symbol of x to the 7th plus cube root of x plus 1 over x to the 4th dx. This means, for now, find the antiderivative of the function inside. X to the 7th plus the cube root of x plus 1 over x to the 4th. So for now, when you see this squiggly looking s and this dx at the end, these are just instructions. That tell us to anti-differentiate. The reason that this is true is because later on, we're going to develop a connection between how we find the area under the curve, which we symbolize this way a little bit more, and how we anti-differentiate. There's a very, very important, it's literally the fundamental theorem of calculus. That's the connection between how you find the area under the curve and using antiderivatives, which we will get to, just not there. But when we write this, we're going to mean find the antiderivative. So go ahead, let's find the antiderivative. And I would recommend rewriting this as the antiderivative of x to the 7th plus x to the 1/3 power plus x to the -4th. Go ahead and find that antiderivative. And I wouldn't worry too much about simplifying your answer, but certainly welcome to simplify your answer if you want to. All right, let's take a look. So for each of these x to a powers, I'm rewriting, or I'm not rewriting, I've already rewritten it. I'm using the anti-power rule, but I have to have rewritten in the way that I have x to a power before I can use that rule. So, right, I couldn't have said the antiderivative of 1 over x to the fourth is 1 over x to the fifth over 5. It's not going to work for me. I have to rewrite this as x to some power. To rewrite this as x to some power. And then for each of these, I can add 1 to the power, divide by the new power. Same deal here. I'm going to get x to the 4/3. And usually what we end up doing is when we see that we're going to divide by a fraction, we start just immediately multiplying by the reciprocal. So in the future, I'll probably say like I have x to the 4/3, and instead of dividing by 4/3, I'll multiply by 3/4 because that's going to happen every time. And then over here, we're going to have x to the negative what? Right. It's easy to make a mistake there because sometimes you think about it getting bigger and saying -5 accidentally, but we know we're adding 1 and -4 plus 1 is -3. And then if I were simplifying this, I would write this as x to the 8th over 8 plus 3/4 x to the 4/3 minus 1/3 x to the -3 plus c. That's how I would choose to simplify that. So we don't just have an anti-power rule for antidifferentiating. There are lots of other things that we are able to find the antiderivative of in addition to powers of x. For example, lots of things. So really the answer is anything that you know how to take the derivative of, the answer to that is something you are expected to know how to find the antiderivative. So we could say something like, we want to find the antiderivative of 2x cubed plus secant squared of x. For the first part, we're going to use the anti-power rule. We're going to get 2 times x to the 4th divided by 4. And as you might have noticed, maybe not, when you have constant multiples, just like with derivatives, if you have a function with a constant multiplied by it, that constant multiple just gets to hang out. And then you do the antiderivative, and then you kind of deal with things in the end. For the antiderivative secant squared, we definitely learned a function in 21A that derivative is equal to secant squared of x. And I think it was what? What was it? It is definitely tangent of x. And then, yes, I would write this as 1/2 x to the 4th plus tangent of x plus c. But I'm not going to. And so that's true for any of the trig functions where we knew the derivative. So another example might be something like if I wanted to find the antiderivative of 3x to the 5th plus cosecant of x times cotangent of x. Well, we're almost there in that we know a function whose derivative is almost cosecant of x times cotangent of x. The derivative of cosecant of x is equal to negative cosecant of x times cotangent of x. Well, I can adjust by a constant multiple. If I multiply both sides of this by -1, that's totally allowed. So it's also true that the derivative of negative cosecant of x is equal to negative, so positive cosecant of x times cotangent of x. So here for anti-differentiating, we're going to get 3x to the 6th divided by 6 minus cosecant of x plus c. And then, yeah, that could also simplify. You're not too worried about that, though. So what things do we need to be able to anti-differentiate? Kind of all the things. I mean, okay, not all the things, but anything from the list of derivatives we know. So I would say there's like, I'd say there's like 12 things on this list. 12? I think 12 sounds right. Let me say what I mean. So yeah, let's just make the list. We can make a list, right? Let's make the list of the derivatives we know and the antiderivatives we're expected to know. I think this is worthwhile. So we know that the derivative of x to some power is that power times x to the power minus 1. And on the other side here, the antiderivative of x to some power, we add 1 to the power and then divide by the new power. And after that, I would say the list consists of trig functions, exponential and log, and then the inverse trig functions. That would be what I think of as the list of things we're kind of expected to know. So we know that the derivative of sine of x is equal to cosine of x. So then I'm going to reverse it. The integral, or I should say antiderivative at this point. The antiderivative of cosine of x is equal to sine of x plus c. The derivative of cosine of x, I like parentheses here, is equal to negative sine of x. So the antiderivative of positive sine of x is equal to negative cosine of x. Let's see. The derivative of tangent of x is equal to secant squared of x. The antiderivative of secant squared of x is equal to tangent of x plus c. Those plus c's are important. Okay, if you know the derivative of tangent, you know the derivative of cotangent. I talked about this last quarter a little bit, but for those of you that weren't with me, I'm going to say it again. For any of these tangent, cotangent, secant, cosecant things, you can kind of take the nicer one, meaning the tangent or the secant one, and add on the prefix co in front of everything to get the other derivative. Meaning, if you know that the derivative of tangent is equal to secant squared of x, the derivative of cotangent of x is equal to cosecant squared of x, but there's a minus sign in front. So then the antiderivative of cosecant squared of x is equal to negative cotangent of x. Okay, you got a few more to go. The derivative of secant of x is equal to secant of x times tangent of x. The antiderivative of secant of x is equal to secant of x. Sorry, I got a little bit at that. So what should I have actually written here? Not the antiderivative of secant, but the antiderivative of what? Right, the antiderivative of the thing that's the derivative there. Sorry about that. So it was looking so nice too. The antiderivative of secant of x times tangent of x dx. That's not the worst thing I've ever written, but that's not saying much. Is secant of x plus c. Let me write that again because I feel like that's a crime. This is the antiderivative of secant of x times tangent of x dx, and it's equal to secant of x plus c. Sorry about that. And then in a similar way, the derivative of cosecant of x is negative cosecant of x times cotangent of x. So the antiderivative of, I'm going to write the right thing this time, cosecant of x times cotangent of x is equal to negative cosecant of x. C. Okay, just a few more. I think there's 5 more, well, 5 or 8, depending on how terrible you want to be. Everyone's favorite, the derivative of e to the x is e to the x. So the antiderivative of e to the x is also e to the x. Let's see. Okay, now here's where things are going to get a little bit sketchy. The derivative of the natural log of x is equal to 1 over x, which is x to the negative first. So there's your x to a power, where the power is the problematic one, where you can't use the anti-power rule. The antiderivative of 1 over x is almost the natural log of x. It's actually the natural log of the absolute value of x plus c. There are reasons for this. The real reason is domain issues. So here, it's totally fine to take the derivative of the natural log of x, whose domain is everything that's positive, and get 1 over x. But it's actually implied here that this derivative is only when x is positive. So in fact, let me grab another piece of paper real quick here. Come back to this in just a second. When we say that the derivative of the natural log of x is equal to 1 over x, you know what I should do? Instead of trying to graph this not wonderfully, let me show you what I mean using a wonderful graphing tool that you all have access to. Second here, maybe I can do it. Yeah, let's do that. So here's what I mean. I can't look there. It's impossible. So here's the lovely graph of, oh, you know, I'm gonna show you something. I think I showed you all this last quarter, but I'm gonna show you again because I think it's cool. So let's say we have f of x equal to the natural log of x. So let's graph the derivative. Check this out. Here's how you can graph the derivative, right? F prime of x. Isn't that neat? I did that. A student showed me that. I thought it was the coolest thing. I was like, really? You can do that on Desmos? But what you're actually graphing there is y equal to 1 over x, but not all of it. Only when the original function is defined, which is when x is positive. So if we change the domain here to be just that, then they look the same. So the derivative of natural log of x is just the function 1 over x, but only for positive values of x. But if you're anti-differentiating 1 over x, so then I'm really curious as to why you can't see the thing I'm clicking on right now to make those not appear. But if your original function is 1 over x, well, that's defined when x is positive or negative. And so when you take the antiderivative, it should be defined on really kind of a larger domain if possible, certainly not a smaller one. So when we do this, and we'll talk more about like how you actually do this, but for now, I just want to show you that when we find the antiderivative, which I guess I'm going to call it capital G of x. I wonder if you can, I'm curious, I wonder if you do, let's check something out. I'm curious what's going to happen here. I really don't know. No, it didn't work. Okay, well, you can hope. Anyway, if we write the antiderivative, it's actually the natural log of the absolute value of x. Which apparently they don't like the fact that I've used capital G of x there. Let's just make that a y. And I don't know why it's not showing up. I'm curious. It says I've got problems. Why don't you want to show up? Use parentheses around the argument of the natural log. Okay, I didn't know how to do that. That seems unnecessary to me, but okay then. So there we go. So there's the natural log of the absolute value of x. It's really just the natural log function, and then you take the right side of it and you reflect it across the y-axis to make it look like the other half of it. But you can see here that on the left-hand side, the slope of any tangent line would have a negative slope, meaning it would have a negative derivative. And this function that is its derivative is certainly having negative values there. On the right-hand side, the natural log of the absolute value of x function is increasing. It's got positive derivatives, and the values of the derivative of that are definitely positive. So the reason you have to define it this way, which I know is kind of a little bit in the weeds here, but the reason you have to define it this way is so that the domains match up. So long story short, when you are finding the I already wrote that over here. when you're finding the antiderivative of the not of 1 over x. Sorry, I've got all sorts of things. When you're finding this, you definitely need the natural log of the absolute value of x. It is not optional. It is actually required. Okay, I think there's only 3 left. Well, technically 6, but really only 3. So you might have learned last quarter, I hope you learned last quarter, that the derivative of the arc sine of x, or if you prefer, the derivative of the inverse sine of x, same deal, is 1 over the square root of 1 minus x squared. Sorry, I've written that kind of small. So on the flip side, the antiderivative of 1 over the square root of 1 minus x squared is the inverse sine or the arc sine of x. I will usually default to writing the arc sine as opposed to the inverse sine just because I feel like it's a less confusing name for the function. So when I write inverse sine, sometimes people mistakenly think that's 1 over sine, which it is not. That's cosecant, different than arc sine. And then we usually kind of ignore the arc cosine, and here's why. The derivative of arc cosine is the negative of 1 over the square root of 1 minus x squared. And if I were to antidifferentiate that, I wouldn't say the antiderivative was arc cosine. I would say the antiderivative was negative arc sine, because that just seems more, it's really what people do. But right, if I want to find the antiderivative of negative 1 over the square root of 1 minus x squared, I could just write that as negative the antiderivative of 1 over the square root of 1 minus x squared. And that's just negative arc sine of x plus c. That's why I was saying there's really only kind of 3 of these, because the arc sine and the arc cosine essentially have the very, very similar antiderivatives. The arc tangent and the arc cotangent also very similar. The arc secant and the arc cosecant also very similar. So we usually only think about really the arc sine, the arc tangent, and the arc secant because they're the nicer ones. So to get those on there, and let me look at one thing here. One thing I want to see that I want to make sure I don't make a mistake on. So the derivative of the arc tangent of x is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is the arc tangent of x plus c. And then finally, and here's where there might be a little bit of weirdness, the derivative of the arc secant of x. How many of you did this in class last quarter? It's okay if you didn't. It's really okay. If you didn't do this, the one reason you might not have done it is because it's terrible and there's not agreement on what the actual derivative is. There's 2 technically correct answers. One of them is 1 over x times the square root of x squared minus 1. One of them is 1 over the absolute value of x times the square root of x squared minus 1. I really, really, really wouldn't worry about it. If your teacher really wants you to know about it, they will make it clear what they expect from you, or they should make it clear what they expect from you. And that's why I was actually looking back at my notes here for a second, because I was trying to remember what the actual antiderivative is, because I don't remember exactly how it works, because it's just not that important. But I'm going to look here because I want to say it correctly. Let me take a real quick look. Yeah. One second. So yeah, so when you do the antiderivative of 1 over x times the square root of x squared minus 1 dx, you do in fact get the arc secant of the absolute value of x, which is a little annoying, but probably not going to come up, to be perfectly honest. And usually when we deal with something like this, to be really, really frank, there's another method of integration we're going to learn to deal with things like this. So I wouldn't worry too much about these last ones here. But I would say this is the whole list. These are all the things that you are plausibly expected to have known how to differentiate in 21A. So all of these derivatives we get to know their antiderivatives are just the thing we differentiated in the first place. So if I said, what's the antiderivative of e to the x? Like, oh, e to the x. So what's the antiderivative of cosine of x? We're going to say sine of x because we know those derivatives already. And the thing I really want to say is, when you're finding an antiderivative, you're just undoing the derivative. They undo each other. If you do, or you take the derivative of a function and then take the antiderivative of that function, you're going to end up essentially where you started, maybe with a constant tacked on. But really, that's kind of it. So the big kind of story here is that, not that, is that antiderivatives and derivatives undo each other. So just for example, if your function is something not terrible, like 4x cubed plus 5x plus cosine of x, I could go either way. I could take the antiderivative, and I'm going to use the capital F notation because it's occasionally good to use. The antiderivative here is going to be 4x to the fourth over 4 plus 5x squared over 2 plus the antiderivative of cosine of x is sine of x plus c. I'm going to simplify that because why not? That's x to the fourth plus 5 halves x squared plus sine of x plus some constant. And if I take the derivative of that, I'm going to end up exactly where I started. The derivative of x to the fourth is 4x cubed. The derivative of 5 halves x squared is 5 halves times 2x. The derivative of sine of x is cosine of x, and the derivative of a constant is 0. And then I would simplify this and make it 4x cubed plus 5x plus cosine of x. So they literally undo each other. You do one, then the other, you end up back with the function you started with. If you go in the other order, if you were, say, were to differentiate first, so if I were to find f prime of x first, the derivative of this is going to be 12x cubed plus 5 plus negative sine of x, or just minus sine of x. And then if you anti-differentiate that, the antiderivative of f prime of x, well, again, I'm just going to use the antiderivative. So it's going to be 12x to the fourth over 4 plus 5x minus the antiderivative sign is negative cosine plus c. We do end up with a slightly different answer than what we started with because there's going to be a plus c at the end. But we're going to get, oops, I think I made a small error here. Did I make an error? I think I did make an error. Do you guys see the error? I know it's kind of hard to see because the functions are up here, but what's the derivative of 4x cubed? Without looking at what I wrote that's wrong. 12x squared. Oh, 12x squared. Not 12x cubed. Sometimes I make mistakes. It does happen. If you see it, you think something's wrong, just call it out. I know I make mistakes. I'm not offended. And also if you think something's wrong, but it's actually right, that's also okay. Everyone makes mistakes. So this really should have been not 12x to the fourth over 4, but 12x to the third over 3. Sorry, I know that looks not wonderful. 12 divided by 3 is 4. And then we're going to get 4x cubed plus the antiderivative of 5. Yeah, 5x, sorry, apologies, plus cosine of x plus c. So when we do the derivative and then the antiderivative, we end up with the exact same function we started with plus the constant. But the idea still holds that when you do both of these things in either order, you essentially end up back where you started. Or as I prefer to say, the two processes undo each other. And that's really kind of the important nature of the antiderivative. It's that it undoes the derivative. And that's what we're going to see when we actually learn the fundamental theorem of calculus, is that the derivative and the antiderivative, by definition, undo each other. Not today, though. I thought there's something else I want to say here. Let me look at my notes. What time is it? I got 17 minutes. Okay. Sure. Oh yeah, there's that. So the other thing that I would encourage you to get comfortable with is something that comes up often enough that you don't want to have to write it out every time. So let's start with this example. The antiderivative of cosine of x, as we've seen a couple times, is equal to sine of x plus c. What about the antiderivative of cosine of 6x? Well, I'm pretty sure it's going to be something like sine of 6x. Because whenever you're differentiating or anti-differentiating, the inside stuff of a function doesn't really change. It's kind of like how with the chain rule, when you're differentiating, the inside part of the function doesn't change, and then at the end of the day, you multiply by the derivative. Well, let's take a look. I'm going to guess. My guess here, which is wrong, is that the antiderivative here is going to be sine of 6x plus c. We're going to fix it, but I'm going to start off with the wrong guess. Okay, let's see. If I take the derivative of that, the derivative of my guess, the derivative of sine of 6x plus c is going to be cosine of 6x, but right times what? Right, plus 0. But I'm off, right? Because the antiderivative and the derivative should undo each other. If I actually had the antiderivative of cosine of 6x, then my derivative needed to equal cosine of 6x. I'm off by a multiple of 6, so what I'm going to do is I'm going to multiply by 1/6 to adjust for that, or divide by 6, whichever way you want to say it. So I'm going to multiply, or I'm just going to rewrite it as the right guess is actually going to be not sine of 6x plus c, but 1/6 times sine of 6x plus c. And I really should throw this pen away because it's really running out of ink. And let's check. The derivative now is going to be, oh yeah, that's going to work because the multiple of 1/6 is going to hang out, and the derivative of sine of some stuff is cosine of the stuff times the derivative of the inside stuff, and then the 1/6 and the 6 end up canceling out. And you might be wondering why I didn't write the plus c there. It's because I'm lazy, and also because I knew the derivative of it was going to be 0. Often when we're taking the derivative of something and there's a plus c at the end, we just don't even write it because we know its derivative is going to be 0. But I should write it because it's proper. So the actual antiderivative of cosine of 6x is equal to sine of 6x divided by 6, or times 1/6 plus c. And the thing I actually want you to really know is that this pattern holds in general, meaning if you're anti-differentiating something basic like sine or cosine or e to something, and instead of x, you have a multiple of x, we typically end up dividing by that multiple of x. So for example, we know that the antiderivative of e to the x is e to the x plus c. So I want you all to make a very educated guess about what the antiderivative of e to the 4x should be. Write it down. Hopefully you all guessed the same thing I did. Even if you didn't know, it's okay if you guessed the wrong thing. But the right thing is going to be e to the 4x because the integral of e to the 4x is e to the 4x. But then we have to divide by 4 or multiply by 1/4. And that's exactly plus c. That's our antiderivative because we can check. If we took the derivative of 1/4 e to the 4x, it's going to be 1/4 times the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the 4 and the 1/4 cancel. So technically, you can always check if your antiderivative is correct by differentiating. The issue is that you have to be able to differentiate it correctly to actually check, right? If you're making mistakes anti-differentiating, you might be making the same mistakes differentiating. But yes, you can always check if something is the antiderivative of something by checking the derivative of the antiderivative. So for example, I could tell you, I could lie and say, let's rephrase that. I could ask you a true or false question. Is the antiderivative of 2x times cosine of x equal to x squared times sine of x? And the way I would check is, well, currently we do not have a way of antidifferentiating 2x times cosine of x. Antidifferentiating a product of two functions requires a method that we will learn later in the quarter. But for now, that's not how we're meant to answer the question. We're meant to answer it by saying, well, let me check. If the antiderivative of this function is equal to that function, I should put a plus c there. Then the derivative of that should be equal to the inside part there. The inside part there, by the way, is usually called the integrand. Just in case people start throwing that word around. It's just the function we're antidifferentiating. So if I take the derivative of x squared times sine of x, what rule do I need to use to take the derivative here? Yeah. So I'm going to get 2x times leave the sine alone plus x squared times the derivative of sine is cosine. And I'm pretty confident that that is not equal to 2x times cosine of x. So the answer here is no. The antiderivative of 2x times cosine of x is not equal to x squared times sine of x plus c. Later on, we will learn how to find the antiderivative, but that's not the point. The point is that if someone's asking you if an antiderivative of a thing is another thing, the easiest way to usually check that is by differentiating the thing that's supposed to be the antiderivative and seeing if you get back to it. In the same sort of way, we could ask the question, is the antiderivative of the natural log of x equal to x times natural log of x minus x plus c? Well, let's find out. We're going to find out by taking the derivative. So let's check. The derivative of x times the natural log of x minus x also requires the product. So let's see. We're going to get 1 times the natural log of x plus x times the derivative of the natural log of x is 1 over x minus the derivative of x is 1. Again, you will note I forgot the plus c here because my brain is just so used to ignoring it, but I should write it down. And let's see, if we simplify this, we get the natural log of x. X times 1 over x is 1 minus 1. Oh yeah, we end up getting the natural log of x. That checks out. So we'll learn later how you find this antiderivative. Both of these require the method that's called integration by parts. But this is the antiderivative of that because the derivative of that ended up being the natural log of x. Cool. All right, so antiderivatives. I would encourage you to practice them. There's lots of practice available. Again, I would check out Cuba's website, Grant's website, or I mean, really first you should do your homework, right? Do the homework. And if you want more practice, there is lots more practice to find. I would highly recommend practicing antiderivatives because the expectation is going to be that you are antidifferentiating these things with ease. Your professor expects that you could say, like if I said, what's the antiderivative of x to the third? It should be like, right, rapid fire. Right? That is what they're thinking that you are capable of doing. Whether that's true or not, we want it to be true because I want you to be able to do it too. Like I want you to have the ability to be like, oh yeah, I know the antiderivative of x to the negative 7th is x to the negative 6 divided by negative 6. Or the antiderivative of secant x tangent x is secant x because we've practiced it. That said, we end at 4:30, right? Okay, I got 7 minutes. All right. Oh, that said, if you ever need to leave early, you are welcome to leave early. You're welcome to come late. You're welcome to use the restroom. You should come and go as you please, as undisruptively as possible. But also, this is the least important class you're taking, right? It might be more useful than some of the other classes you're taking, but it is the least important class you are taking. Every other class you're taking counts for a real grade, probably. So prioritize those. If you have a test before this that runs long, or we have an exam after this that you need to leave early for, that is totally, totally fine. You don't need to check in with me. You can take off whenever you want. And I will be like, they obviously had something that was more important That's totally fine. So don't feel like you need, like if you need to go because you need to catch a bus or go to work or whatever, right? That's really okay. Don't feel like you need to stay here because I am here. So use your, you know, adhere to your schedule as you need to. Totally fine. You won't get marked like absent or late because you, right? I'm just going to look at the form that says, oh, they said they're here. Great, they're here. Okay. Yeah, but and also, yeah, if you need to use the restroom, you should use the restroom as you need to. Totally fine. So we got what, 6 minutes? Yeah, we should talk about. So what we're really moving towards is the next section, which I believe is section 5.1. Yeah. Oh, yeah, sorry. There's so many things to say. Yeah, we should. The problem is I like the start of new, I like it's terrible to start a new thing with 5 minutes left. So I shouldn't do that, even though I want to do that. So here's what I'll say. Next class, we will talk about estimating area under a curve, finding area under a curve, talking about the limit definition of the integral probably. For now, with these last 5 minutes, what I would like to ask though is for you to find the following. I want you to find the antiderivative of, where'd you go here? Yeah, let's say e to the negative 5x plus secant of 3x tangent of 3x. Yeah, find that. I like that question. All right, so we got. So whenever I'm doing derivatives or antiderivatives, I'm really thinking about like the version of the rule of just x, and then I'm modifying them. So when I'm looking at this, what I'm really thinking of is I know the antiderivative of e to the x is e to the x. So the antiderivative of e to the stuff is going to be e to the stuff, and then I'm going to divide by -5. Similarly here, I know the antiderivative of secant x times tangent x is just secant of x. So the antiderivative of secant of some stuff times tangent of the same stuff, it doesn't have to be the same, is going to be secant of that stuff, and then I'm dividing by 3. And then I would probably rewrite it as like -1/5 e to the -5x plus 1/3 secant of 3x, but it doesn't matter. I want to make sure I haven't led you astray or led you down a thought process that might be incorrect. So I want to point out that this idea of dividing by the thing only works when the thing you're dividing by is a constant. What I mean is that if someone asked you, what's the antiderivative of e to the x squared? Well, first of all, they're unkind because it is not antidifferentiable. This function does not have a nice antiderivative. It's like the most common example of a function that we cannot find the antiderivative of. There are lots of functions that don't have elementary antiderivatives where you have to write it in some weird kind of funky way. But I want to point out this is not e to the x squared divided by the derivative of x squared. That nice pattern that we've been seeing for those only works when the thing you're dividing by is a constant, not some other function. Because if you try to differentiate this, you'd have to employ the quotient. And the derivative here is going to get much, much messier than just e to the x squared. Whereas here, to take the derivative there, you really just have constant multiples. So if you have -1/5 e to the -5x plus 1/3 secant of 3x, let's see, the derivative, those constant multiples just hang out. And the derivative of -1/5 e to the -5x is -1/5 times e to the -5x times -5. And the constants cancel. Same deal here. The derivative here is 1/3 times secant of 3x times tangent of 3x times 3, and the constants cancel. So that's why that nice little kind of pattern works for things where you have a constant multiple of x, but not for things where you have a more complicated function of x replacing x. All right, it's 4:29. I should stop saying words. I'll see you all on Thursday. And I will post the notes on Canvas, and I will also, oh my gosh, post the recording of the lecture once it becomes available. And have a lovely rest of your day. Stop the thing.